quadratic functions are something I think you're going to be familiar with. So just a reminder, a linear function, which we also call a first-degree polynomial, is something in the form f of x equals ax plus b, and its graph is a straight line. Whereas a quadratic function is a second-degree polynomial, and it has the x squared term. So it's f of x is ax squared plus bx plus c, and the graph is what we call a parabola. It has one turn to it. I'll come back to that later about the one-term business. So some examples of some quadratic functions: x squared plus 2x plus 3. Here a is the understood 1 in front of the x squared, b is 2, c is 3. G of x, negative x squared plus 4x subtract 4. A is an understood negative 1, b is 4, and c is a negative 4. Be sure you don't miss the sign. That will make a difference. And in this case, h of x equals 2x squared subtract 2. Because there's no x term, a is 2, and c is negative 2, and b is a 0 because of the missing x term. Characteristics of the graph: if the a value, the number in front of the x squared, is positive, we get a smile for our parabola. It's a parabola that opens up, and the vertex would be the minimum of the function. If a is less than 0, we get a frowny parabola, and the vertex is the maximum of the function. The graph will always have one y-intercept, and it'll be the constant value of the function. The graph may have two, 1, or no x-intercepts, and we find those by setting the function equal to 0. The graph is symmetry to a vertical line through the vertex. We call this the axis of symmetry. It will always be x equal the x-coordinate of the vertex. So getting specific, to find the vertex of a parabola, which is a point, so it needs both an x and y coordinate. We call them h and k. We find the x-coordinate is negative b over 2a, and then we plug that value back into the function to find the y-coordinate. Or, if you know some calculus, it's the first derivative. If f of x is x squared plus 2x plus 3, negative b over 2a is negative 1, plug that x value back into the function. Looks like I forgot my negative here. Do the calculation to get the y, and then the vertex is at negative 1, 2, and the axis of symmetry is x equals negative 1, the vertical line through the vertex. A couple more examples. Negative b over 2a in this case would give us x equals 2. Substituting the 2 in. Watch the negative on here. We have to first square the 2, then apply the negative. We'll end up with 0 for the y-coordinate of the vertex. So vertex is 2, 0, and the axis of symmetry is x equals 2. So it's always x equal whatever the x-coordinate of the vertex is. And then our third example, since b is 0, our x-coordinate of the vertex is just 0, which gives us negative 2 for the y-coordinate, and then the vertex is 0, negative 2, and the axis of symmetry is x equals 0. Okay, looking at those same examples, finding the x and y-intercepts. X-intercept is just the constant, so in this case it's the value 0, 3. And to find the y-intercepts, we set the function equal to 0, solve, and in this case we can see the discriminant is negative. 2 squared subtract 12 is going to be negative. So our solution to this equation is going to be an imaginary number with an I in it. But if we're actually looking for the x-intercepts, we're only interested in real solutions. So in this case, we could just stop and say no x-intercepts. Our second example, the y-intercept's a negative 4. The x-intercept we can find by factoring. And notice, personally, I hate it to factor when my leading coefficient's negative, so I just moved everything over to the left side of the equation, set it equal to 0. For me, it's much easier to factor that way. Notice we're getting identical factors here, so we're only getting one solution, 2, 0, and so we have one x-intercept in this case. And then our third example, the y-intercept is 0, negative 2. Solving, we get two x-intercepts, negative 1, 0, 1, 0. And we could easily check all of this with a graphing calculator, something I probably should have done. I hope I haven't made any silly arithmetic mistakes. And then just a couple quick story problems. Points of interest are usually the vertex, because it's the maximum or minimum of the function, and the intercepts. Interesting things happen there. So here's a classic falling object model, rocket shot into the air. Since we're interested in how high the rocket is in the air, we're interested in the vertex. So we can do our formula. to find 2 seconds for the x-coordinate of the vertex, but that's not the piece of information we want. We want to know how high it actually is. And to get the height, we have to plug the time back into the function and calculate height, which in this case is 64 feet. So the rocket reaches its maximum height of 64 feet 2 seconds into its flight. And of course, I've given more information here, my answer than was actually asked for. The only piece of information I really needed to give is that the maximum height was 64 feet. The time when it hits the ground, when will it hit the ground? So that's time. When it's on the ground, its height is 0, so set the height equal to 0, solve, we get t equals 4, and the rocket hits the ground after 4 seconds. And I didn't write the rest of the question up here. So the number of radios sold depends on the price. So the number of radios X is 1300 subtract 100p, and the revenue is the number of radios times the price. So the number of radios is 1600 subtract 100p, and the price is p, and that's what gives me a quadratic function for the revenue. And I went ahead and rewrote it so it was in standard form with the p squared term first followed by the p. In this case, c is 0. So the maximum revenue occurs at the vertex, negative b over 2a. Do the calculation, 6.5. I failed to put any units into this problem, so I'll just assume the maximum revenue occurs when the price is $6.50. Okay, modeling using regression. In your textbook, it lays out the steps of how to do this on your calculator. So just a couple comments. The real world data, there's usually not a perfect linear fit to a model, but there's usually a trend which appears to be linear, quadratic, exponential, etc. The least squares regression line your calculator will find for you, which is nice because this is actually the formula for finding the values of a and b on what your calculator does for you. So if you're interested, here are the formulas. You don't need to know this. And here's the data and what I did on the calculator. And if you check on the activity that we're doing for this first paper, this is what I used for the activity report in the rough draft that I gave you for an example.